Good afternoon, everyone. Welcome to join this session. I hope you have a good summit and good trip in Vancouver. Today is the last day of the summit session, and in this session, I will share with you about the optimized HPC and AI cloud with OpenStack Acceleration Services and compatible hardware. And Jianfeng from Intel, he will with me to talk about this topic. I will first of all share with you about the compatible composable hardware, which is leverage the Intel rack scale design architecture. And Jianfeng will share with you about the acceleration services in OpenStack.
Yeah.
Jianfeng, do you mind you give a brief introduction about yourself?
Yeah, sure. My name is Jianfeng Ding. I'm from Intel. I'm working on the OpenStack upstream projects. For this presentation, I will talk about the accelerator devices management services. The name is Cyborg. Maybe somebody has already know about that. Yeah, thank you.
Okay. My name is Shuquan Huang. I'm from 99 Cloud. 99 Cloud is founded in 2012 in China. We are working on OpenStack hardly. We provided the OpenStack services to our customer and provide a solution based on open source project to resolve the real world problem for our customer in China. Right now, our new direction is move to edge computing. So we will also working on some edge projects such as Crano, Starling X, such projects. Okay, today's agenda. First of all, I will introduction the AI HPC workload challenges. What kind of workload we are going to meet in the future data center, and do we have the solution to resolve those problems? What kind of technology we can use? And then I will give the introduction about the Intel RSD technology, and I will show you the demo afterwards. And then Jianfeng will introduce the OpenStack Acceleration Service Cyborg and the future plan. So let's take a look at the future technology happening here. By some reports, we can see there will be 50 billion connected devices happening in 2020, and all those devices, they may connect with the 5G wireless and other networking. So many devices they connect together will generate a lot of data. So in the cloud, normally we are doing the web hosting, some simple IT applications, but maybe in the future we will apply so many analysis work and machine learning algorithm based on those data, so we can get the detail, get the knowledge from those data. So the HPC and AI work in the data center will be a necessary and not an option. So at the before, maybe we can still use the CPU to compute those data, consume those data, but in the future, we have to use the hardware acceleration. As we know, there are many types of devices for the hardware acceleration, such as GPU, ASIC, NVMe, and FPGA. But how can we manage them in a framework? How can we manage them in an OpenStack? That is a problem. Before, maybe we know we can use OpenStack to use GPU, but there is issues over there. We have to configure it in the normal computer config file, and we have to check the vendor code of the PCIe devices and input them into the file. That's not flexible. So we have another services, acceleration services, to help us to manage all those devices very flexibly. And on another side is that traditional hardware architecture is not flexible enough. We have to need another composable hardware to help us to deliver those high-performance hardware to the customer so that they can run all the application on top of it. So we have another new next generation technology for those hardware. We call it the composable hardware, which is leading by the Intel RSD technology. Intel RSD technology is based on a standard implementation, such as the Redfish management API and the storage management API, Swordfish. And on top of it, we are building those standard on the existing solutions, such as OpenStack and Kubernetes. Take OpenStack, for example. We are implement the RSD library in the Ionic so that we can use Ionic to manage all those RSD servers. And we also can use the Horizon to talk with the RSD library to manage all those RSD compatible hardware. There are many OEMs implement RSD standards such as the Quanta, the Inspur, Huawei, and many others. And on top of it, we can use the pooling resources to meet the requirement of the application. If we are going to need a high-performance storage, we can use the RSD to help us to compose a high-performance server with NVMe drive. And we can have the high-performance storage. And also, we can compose with GPU and FPGA as well. So combine the RSD and acceleration services Cyborg of OpenStack, we can very flexible to manage all those acceleration and hardware in one place. Let's take a look at the RSD roadmap. 99 Cloud work closely with Intel on RSD. From the 2 years ago, we are work with Intel in RSD 1.1 version. At that time, we can use the OpenStack to compose all the physical nodes. We can select the number of CPU, gigabytes of the memory, and the capacity of disk, and compose a server. And then we will enroll this server to Ionic. Ionic can deploy operation system to those servers. And in the 2.1, we enable the NVMe dynamic allocation features in the OpenStack by integrating with the 99 Cloud OpenStack solution. I will show you a demo afterwards. You can see we can just attach the NVMe driver as we use the single function to attach a virtual disk to a VM. It's very simple to get a high performance storage in your compute. And in the future, the 2.3, which is targeted in the Q2 of this year, we will get the NVMe over Fabric so that we can have a large scale cluster. They can get the high performance NVMe over the Ethernet or RDMA protocol. So we have seen how the Intel deployed this simple server disaggregation for more times in the data centers. And the Intel RSD, it takes the concept further by enabling this disaggregation for rack storage application by using the PCIe and NVMe protocol. And the control information is communicated among the RSD components through a dedicated Ethernet management network connecting all the resources in and access those racks. The data channel is provided by NVMe PCIe channels between computer resources and the NVMe resources. Typically, there is an NVMe switch between compute and storage modules to enable flexible composition of the resources. The NVMe and PCIe approach provides a very high bandwidth and low latency, which is particularly important for SSD storage resources. Traditionally, we have to use iSCSI and SAS interconnects simply cannot take advantage of those performance of the new storage technologies. And the downside of using the PCIe, as we can see, there is limited by the length of the cables. So we have the NVMe over Ethernet technology, which will come in the 2.3 version. It will expand the scope of the NVMe storage performance for us. So I will introduce you these two implementations in detail. First, we can see the direct attached PCIe storage pooling. This is use the required PCIe terminal cards in the computer server, and when we send the attached command, it will actually go through the PCIe, and you will use the PCIe directly attached to the computer resources. So the computer resources will see actually you have attached NVMe by the PCIe. You get the highest performance and the lowest the latency. But in this implementation, they limited by the length of the cable. And we can, if you have a large data center, you like to attach NVMe from a another rack which is located very high away, then you can use the NVMe over Fabric implementation. In this implementation, they have two methods actually. One is based on software. You use the software to simulate the RDMA implementation. So when you attach, actually you are leveraging the software to do it. So this is not the modest, this has a worse performance than you use the hardware-based storage pooling over Ethernet. If you have the RDMA card, you can use the hardware-based storage pooling over Ethernet solutions. But you have to install every RDMA card in each compute resources. When the RSD port manager is sending the command, it will use the PNC module to control all these attachment and use the RDMA protocol to attach the NVMe resources. Okay, let me show you the demo about the whole process. This solution is based on the 99 Cloud Anibus OpenStack 6.0. We integrate with the Intel RSD technology. In this demo, you will see how we compose a compute node, and then we attach NVMe storage through the PCIe solution, and you will see we can test it. The driver is a very high performance NVMe drives. First of all, we will add the RSD port manager into this environment so that we can manage all the resources belong to this port manager. We'll input the API address and the username password. After we get the information from the port manager, we will get an overview with this port manager, see how many storage it has, how many computer resources it has. And then we are going to compose a new node. We will input a name, number of the CPU, and the memory and storage you want. After confirm, the port manager will help us to find most suitable resources for us. Right now, we get a bare metal so that we will enroll it to Ionic. We will assign the RAM disk and kernel to this bare metal. So the Ionic will use those two things to deploy the operation system for the bare metal. Right now, you can see Ionic has enrolled. We will automatically create a new hypervisor new item in the hypervisor, and we will create an instance for this bare metal. We will select an operation system, which is Ubuntu, and we will select the flavor, network. Right now, we are creating the Ionic instance. The RAM disk will will send the API with Ionic conductor, and it will pull the image from glance and download it to the bare metal. And the bare metal will reboot. After 2 times reboot, we will get this instance up. As you see, the driver is Redfish, so we are using the RSD Redfish interface to talk with the pod manager. It takes time here because we have to download all the image from the glance and DD to the bare metal. It takes about 15 minutes. After the instance is up, we can use the fixed IP to access this instance. We will see how many disks it has in the operation system. Right now, there is only one. If your application going to have AI or HPC workload, you might need NVMe storage. So right now, we can attach the NVMe storage to this instance. We can just like we use Cinder to attach an instance, to attach a disk. As you see, we get NVMe disk drives in the instance. If you need more, you can attach one more. So in total, we have 2 NVMe drives. After you finish the workload, you may need to reclaim all the resources. So you can detach the NVMe storage, and it will return to the pooling resources to let other users to use it. So by leveraging the RSD technology, you are very flexible to operate all the hardware resources with very convenient ways. So that is why we call it composable hardware. So we mount this NVMe drive and test its performance. After we finish the job, we can even delete the Ionic instance and the bare metal instance from the pod manager to release all of them. Okay. Okay, and we will have Jianfeng to introduce the OpenStack Acceleration Service Cyborg.
Okay, from last summit in Sydney summit, the Cyborg project has become mature to support many accelerator devices. We know Cyborg is a relatively new project in OpenStack. Its target is to provide a generic purpose accelerator devices management services for all the OpenStack clusters. The supported accelerator devices can be some crypto cards from GPU, for some FPGA devices or some ASIC accelerators. For example, the QET devices from Intel. And besides all the hardware accelerator devices, Cyborg can also support the software acceleration library. For example, the DPDK or SPDK. It's very flexible. For the collaboration with Nanan Cloud Shuquan, we have in the roadmap, we want to use the Cyborg to manage all the NVMe devices, the NVMe high-speed storage devices also. So that's this is the feature in our roadmap for this year. Just now, Shuqian has mentioned in 2018, the Intel RSD hardware product has one very important feature. It's NVMe storage over fabrics. So for both the software and the hardware, the NVMe storage support is very important. So that's the reason we continue that. In this page, this architecture, the diagram, we can see the Cyborg can have several layers services. The top one is the Cyborg API. The Cyborg API services can provide several API for the user, for applications, for the operators, etc. And then the API will call the Cyborg conductor services. In this layer, the Cyborg services can store and to collect all the accelerator devices information in a database. Then the Cyborg agent. For every compute node, Cyborg will run a separate agent services in a single every node compute node. For the actual hardware operations, the agent will call some specific drivers to do some operations. For example, currently, one more thing. Currently, in the Cyborg community version, we have already enabled the Intel FPGA devices. So we can take the FPGA devices as a sample how the Cyborg to operate the hardware devices. So the Cyborg driver can do some for example, programming, discovery, and attach operations over FPGA devices. I think this is a very important value of the Cyborg Cyborg services. Also in this diagram, we can see for different type of hardware, we will provide Cyborg will provide different kind of drivers. For example, we have a GPU driver. We have FPGA driver. Also, we will have a NVMe storage driver. this picture is going to talk about the workflow of Cyborg services. It's similar than the previous slide, but the viewpoint is a little different. The most valuable information from this page is the workflow. At first, for one cycle of operations, the user or the application will call the API of Cyborg services, and then the Cyborg services can to talk with Nova services scheduler or Nova not Nova, it's placement services. It's to collaborate with these services together for the scaling support for hardware. And after the calling passed on to the Cyborg agent and the Cyborg driver, the Cyborg driver can do all the hardware required operations to be prepared for the virtual machines. And then whenever the hardware was prepared according to the request from the users, the Cyborg agent can continue to do the devices attach operations to the virtual machines. Okay. Let's go next page. Yeah. Here, this diagram is specific for the NVMe devices support. It's our current design for the NVMe high-speed storage. The workflow is similar. For example, the user or the operators or even some SDK callings will call the Cyborg API to request a new virtual machine with a flavor of NVMe SSD. Then the Nova API will talk with the Nova scheduler, Nova conductor to search the available compute node with the available NVMe devices. One more thing, we can see for every machine in the boot time, the Cyborg will scanning all the supported hardware to discover all the available devices and send the message to Cyborg conductor to record all the information to update the inventory list for that. Let's continue. Whenever just now we talk about the step 2, and the next step is the actual virtual machine creation by Nova Compute services, and then Nova Compute services will talk with the Cyborg agent to get the information of the hardware. And the Cyborg agent can do the attach or some refresh or upgrading operations against the devices. And finally, the user can get a virtual machine with requested hardware to be attached. Yeah, for the current design, it's specific for the NVMe devices. Yeah. Okay, that's all. That's all what I talk about the Cyborg support for the Intel RSD solution. Yeah.
Okay.
Yeah. Thank you very much.
Thank you, and we have 10 minutes left. If you guys have questions, please go to the mic so that we can hear.
I'll give one to you. I feel like singing Elvis Presley holding this. But anyway, it wasn't until the last slide you began to answer the question I had is that a few days ago I was at the presentation about Nova doing their virtual GPUs, and my question is, with two different projects looking at AI, how are you communicating with them to make sure they're not leaving holes in the overall architecture, you're not doing redundant work between the two projects?
Are you asking for the vGPU support in Create Nova code?
Yeah, about the vGPU. I mean, I just simply put, not even just the details, just the fact that you have two different OpenStack projects working on related areas. And I just want to know how good OpenStack is at your projects are just communicating.
Yeah, you're right. As I know, the vGPU support in Nova, and also we know also in LibreVert enabling. This work has been started 2 or 3 years ago. But the Cyborg is relatively new. Yeah, we have launched the new project Cyborg in 1.5 years before. The old name is Nomad, and 1 year before we renamed the project name from Nomad to Cyborg. So Cyborg is new, and the vGPU support in Nova is relatively old. But the GPU support has been done recently. So in the future, I'm not sure which one can be the most proper way to support GPU devices. Yeah, let's see. Yeah, as I know, in the Cyborg roadmap, the GPU support also in that.
Yeah, I think it's a very good question. I can add something from my point of view. I think the vGPU is actually different from GPU, right? It's virtual. So in Nova, it supports virtual GPU, and it depends on the hardware to for the virtualization of the GPU, such as the NVIDIA grade, I think is support, and the KVN GT, yeah, is support. But from the Cyborg, to enable you use the physical GPU, you can just use it alone, not share with others. So that is different level.
I have quite a generic question regarding the philosophy of Cyborg, because it is supposed to provide accelerated services, but accelerated, it means something works faster, yes? But the 3 different use cases we already have right now, which are the NVMe's, GPUs, and FPGAs, these are very different beasts, yes? One provides a block storage, which is basically block storage. Okay, it's faster, but it's still block storage. Maybe sometimes you can treat it as RAM. Yes, so it's not exactly block storage because it's very parallel in access. On the other hand, you have a GPU, which is a sort of processor. Yes. Okay, it's parallelized, but it's a processor. It's very different than storage. And on the third hand, you have FPGA, which is another kind of processor, programmable, very different from a GPU or from an ordinary processor.
Yeah, sure.
And you want to put it, and the project is supposed to put all those different things under a common head. It's a little bit as if you wanted to put Nova, Cinder, and I don't know what under a common project.
Yeah, very good question, actually. Even besides the hardware you have mentioned in the question, the Cyborg can even support the software acceleration libraries like DBDK. So it means Cyborg has its special value for the management support for different devices. So I think the Cyborg can be considered a generic hardware devices management services. Can offloading the management the burden from Nova. According to the message from Nova community, I can feel Nova community like to offloading this effort to Cyborg, according to recent discussions. For example, take example the FPGA support. If we want to support FPGA device properly, we need we need some services or some agent to do the programming support for the operators. But who will do that? I don't think Nova want to do that. So we need a separate or some special services to do that. Then for the FPGA support, Cyborg is a good choice, and and then we can populate the value to some other devices like QET, like NVMe storage. We can, and also for the PCI SRV devices also. Yeah, Cyborg can cover that also. Though the Nova has already supported SRV a long time before. Yeah, I think this some effort can make the Nova more solid, more clean.
Yeah, I think let's go back to see why Cyborg, this project has born. It is because when you are going to use GPU in Nova, it's not an easy way. So you have to do a lot of configuration, right? And as many other acceleration devices. So there is a new project here to help you to have a better way to manage all the devices, because those devices are actually not necessary when you put a virtual machine or a bare metal. So if you already has a virtual machine or bare metal, you want to accelerate the performance, then you have a new project to help you to manage those devices you would like to use. So Cyborg comes out and he manages all those other devices, let you to conveniently use them. Okay, so thank you.
Thank you, everybody.